Hello everybody. So far we have discussed the elastic analysis as well as the different plasticity model, and normal elastic analysis I have covered the isotropic elasticity, but I have not gone through details in anisotropic elasticity. But in plasticity model, that means how we can develop any plastic deformation model, and specifically when it is unidirectional or if it is subjected to some kind of a 3-dimensional state of the stress. So, in both the cases we can develop the plasticity model, and normally I have gone through that von Mises yield conditions, and we can define the yield surfaces when the system is subjected to some multi-axial loading conditions. So, now once we do the elastic analysis and plastic analysis, maybe next point is most significant is the residual stress generated during the manufacturing process. Actually, most of the manufacturing process, it is associated with some form of the residual stress. But what we can analyze the residual stress and what are the consequence effect, and what way we can reduce in perspective of the different manufacturing process, that we will try to explain in this part. So, residual stress, but before details about the residual stress, we can start with these things. We know that expansion and contraction of a model when of a materials or specifically metals, when it is subjected to some kind of the thermal load. That means, if we heat a sample, it will expand, and once it is expand, and if further cool the sample, then it will contract. So, this expansion and contraction actually leads to some kind of thermal strain, and then thermal strain is associated with some kind of a thermal stress, and of course, this thermal stress, if this thermal stress exceeds the yield point of a particular material, that means it enters the plastic deformation zone, then some amount of the permanent residual stress or permanent stress will be generated within a component or sample. Now, most of the manufacturing process, it is subjected to some kind of the heating and cooling, because in manufacturing process normally we apply some sort of the heat source to perform a particular manufacturing process, and then of course, after heating get desired temperature achieved, then it automatically cools to ambient temperature. So, therefore, it is subjected to heating and cooling in associated with most of the manufacturing processes. And of course, if you look into the thermal expansion properties, so that we have already discussed thermal expansion coefficient, and that thermal expansion coefficients we can see that in case of mild steel, this is the value of thermal expansion coefficients 11.8 micrometer per meter Kelvin, or we can say that 11.8 into 10 to the power minus 6 meter by meter and per unit degree Kelvin, or we can say it is a simply per unit temperature change. This is the value of the mild steel. So, in case of zinc, that thermal expansion coefficients, or we can say the contraction coefficient is much more as compared to the mild steel. So, therefore, the stress generates during this deformation, and in case of mild steel and in case of zinc should be different, because in both the cases that thermal expansion coefficients, there is a wide variation, almost 4 times zinc as compared to the mild steel. So, that what we can estimate this thermal stress and strain during the process, if we assume this thermal strain is simply coefficients of thermal expansion into temperature difference. So, basically that delta T particular this delta T, and this delta T is a difference as a particular point, maybe 0.1 and 0.2 in between, what is the temperature difference that actually induce some amount of the thermal strain. So, if it is the thermal strain, and of course, we know the dimension of the thermal strain is basically dimensionless. So, delta T is per unit temperature difference Kelvin, and coefficient thermal expansion is 1 by Kelvin. So, basically it becomes dimensionless. So, delta L, so that means suppose this is the sample size and it is room temperature is T0, and it is temperature raise of this sample T0 to, for example, T1, such that T1 greater than T0, that means raise the temperature. So, therefore, initial length L, we assume expansion happenings in this direction delta L. So, that delta L, that means due to the temperature difference, and it will expand in particular direction. So, that delta L, we can say that strain is basically delta L by L. So, therefore, delta L equal to L into strain. So, L into strain equal to L alpha delta T. So, this is the increment of the length due to the application of the thermal load, or maybe due to the application of the temperature difference between these two points. Maybe for the whole sample it is like that. We can treat initial temperature was T0 and it raised to temperature uniformly to T1. So, it will expand simply. So, that expansion, if we assume that expansion happens only one direction, then we can estimate what is the increment of the length on particular direction. So, that it is when it is subjected to some amount of the temperature difference. So, here we can see these things, but this change of length, or maybe this, if it is free to expand, so there is no restriction on constriction. So, therefore, if it is free to expand, then it will not induce any kind of stress there also. But if it is restricted, that means if we put some restriction and initial temperature is T0, and if we raise the temperature for the whole body T1, but there is some restriction, then it will create the thermal strain. That thermal strain we can estimate in this way, L alpha T, and corresponding thermal stress can be estimated. If we assume stress is proportional to the strain, then stress equal to Young's modulus into alpha delta T. This is the thermal strain. So, this is the amount of the stress. Now, point is whether yielding will happens or not during the restricted component, that means if we put some constant and if we increase the temperature. So, during cooling phase, if the stress value is below the yield point of a particular material, so that means within the elastic zone. So, even if we remove the thermal load, then it will after cooling it will come back to the ambient temperature. So, there may not be any kind of permanent stress there. So, it will come back to the initial position. So, therefore, it may not subject to some sort of residual stress, because within this temperature difference if the phase transformation also negligible. So, therefore, this may not associated any kind of the permanent stress, but if this temperature difference is too high, or maybe in particular material alpha is very high value, or particular material Young's modulus is more, then maybe if this stress sigma cross the yield point value, and then even if we cool the sample, then once it cross the yield point value, so some amount of the permanent stress will be generated within this body, and even we cool the ambient temperature. So, some permanent deformation exists within this body, and that permanent deformation will induce some amount of the stress. So, in general, that is the measure of the residual stress during this process. So, therefore, residual stress will be there if with the application of the thermal load, even in absence of some kind of the mechanical loading conditions, that it can induce some amount of the permanent strain or stress if the stress exceeds the yield point of a particular material. Now, residual stress can be looked in that way, that we can define the residual stress in that way, that internal stress is created, and of course, that internal stress stays inside the body, inside the metal, even after manufacturing process, after completion of the manufacturing process. So, that stress is termed as the residual stress, and in other way we can say that it is a kind of locked in stress, and can be defined the stresses existing within a body in absence of any kind of external load, or in absence of any kind of temperature difference or any kind of thermal gradients. So, that lock in stress is normally defined as the residual stress. So, most of the manufacturing process is associated with some amount of the residual stress, because it may be subject to some amount, either some amount of the plastic deformation happens, or there may be some amount of the phase transformation, one phase to different phase, or maybe phase means from solid to liquid, or then liquid to come back liquid to solid, or some solid state phase transformation, all may induce are responsible to induce at least some amount of the residual stress in a manufacture component. So, therefore, most of the manufacturing or components such as our manufacturing processes, even in casting, and then casting is associated with the melting of a material, and then solidification happens. Then even welding also, welding with if we melt the material, and then after melting it's when we cool it, it come back to the ambient temperature. So, it is subjected to some kind of the phase change, then liquid phase to solid phase and vice versa also. Even for machining may be subjected to some kind of the solid state phase transformation, or some kind of the high strain rate, they can also induce some amount of the residual stress also. Molding, heat treatment process associated with, in heat treatment process normally we reduce the amount of the residual stress, but it alters the residual stress. Of course, in metal forming also, all these basic manufacturing processes introduce or induce some amount of the residual stress. And of course, the residual stress also comes from the metallurgical changes. So, metallurgical changes inside the body, that means induce the residual stress after solidification or solid state phase transformation. Both are responsible to induce some amount of the residual stress in a manufactured component. So, therefore, in general, if residual stress could be caused or may be caused by the local, it is a very localized position, if the yielding of the material happens, even it is not necessary the yielding may happen as a bulk, but in its localized area, if yielding happen, that also induce some amount of the residual strain in the manufactured component, that is in general. So, in principle, deformation gradient, that means the deformation not uniform in a particular direction, if there is some gradient present there within the component, and that deformation gradient, if it is created by the thermal gradient or some amount of the volumetric change or phase transformation, it happens during the solidification, or phase transformation if happens during the solid state deformation, that also induce some amount of the residual stress. Even in solid state deformation, due to the transformation, so some sort of transformation induced plasticity, the metallurgical changes happens. So, that transformation one phase to another phase, that actually it is a very localized, and if it is very micro scale, maybe lower scale, that induce some amount of the plasticity. So, that transformation induced plasticity is also responsible to create or to contribute the formation of the residual stress within the structure. Of course, apart from that, different thermal expansion coefficients, all are responsible factors to create the residual stress in a manufacturing component. Of course, both heating and cooling path in general, if we look into the common manufacturing process, most of the cases it is associated with some heating cycle and the cooling cycle. Apart from the heating and cooling cycle, if application of some constant, that actually induce some amount of the residual stress. Constant in the sense, practically, for example, if we clamp the components before in welding process, so that clamping process itself mathematically induce some amount of the constant condition, and that actually influence the amount of the residual stress generation in this apart from the heating and cooling cycle of during the manufacturing processes. So, residual stress normally we measure using some X-ray diffraction technique and hole drilling method, strain gauge technique, all the mechanical method and these things, and of course, ultrasonic method and magnetic methods are also used to measure the residual stress, but in principle in X-ray diffraction we normally measure the residual stress on the surface, and of course, in the hole drilling method is the mechanical method, we just simply create the small hole within the component, and that component even in depth direction we can measure the residual stress. Normally in hole drilling method, if the release of the stress during the drilling process, that actually induces in the strain gauge some amount of the strain, and that strain is converted to the stress value. Even similarly, strain gauge technique can also be used, just simply using some strain gauges we can measure the residual stress. Of course, in that case some specific methodology techniques have to be developed using this, but in principle in using the strain gauge we measure the strain, and that strain is converted to the stress amount, and that stress is the measure of the residual stress. Now, we can give an example also, residual stress example. Here we can see that residual stress pattern, and we can keep this example in case of fusion welding process. And here if you see, this is the typical profile, we can assume this is the typical profile of a welded zone and for a component. So, therefore, residual stress is present across the unrestricted butt weld. So, it is a butt joint configuration. If we assume the butt joint configuration means two plates are joined together, and it creates this kind of the material volume, and melting volume, and then if we do not put any kind of the constraint and if you do not put any kind of restriction, then also it will changes some amount of the residual stress, because some metallurgical changes happens during this process. So, that it creates typical the tensile type nature of the residual stress, this the direction distribution, but to equilibrate this temperature distribution, then it some compressive residual stress also generated the surrounding of the old metal pool. So, this is the typical nature of the residual stress. Of course, this nature of the residual stress is affected by the restraint condition. So, if we put the displacement boundary, if we restrict the displacement of this boundary of the component, then it influences the amount of the residual stress generation. Now, we can look into some overall aspect of the residual stress. So, residual stress actually important when try to assess the fatigue life of a particular component. It is to estimate, or it is very much influence, actually its residual stress is measurement of the residual stress is very much significant if we try to assess the fatigue life of a particular component. Fatigue life means if the metal is subjected to some kind of the cyclic loading conditions. So, in that conditions, if there existence of the residual stress within the component, the life of the component can be reduced or normally reduced. So, therefore, it is quite most of the cases is quite objective to remove the residual stress such that we can improve the fatigue resistance of a particular component. But in general way, to improve the fatigue resistance of a particular component is to promote the compressive residual stress and try to avoid the amount of the residual tensile residual stress, and that is the most of the cases we can find out. So, even it is not possible to completely avoid the formation of the residual stress in a manufactured component, but what we can do that to change the tensile residual stress to compressive residual stress. If it is possible to generate the compressive residual stress, then it is always advantageous, and that advantageous in the sense that it normally try to improve the fatigue life of a particular component. So, therefore, it is remember the residual stress is actually in equilibrium within the body, and when it is in equilibrium within the exist within the body, but without application of the any kind of the external load during this process. So, therefore, widely used mechanical processes. So, when you manufacture the component, if we follow some simple methodology such that we can improve the generate some kind of the compressive residual stress, or maybe other way we can try to reduce the residual stress in a particular component. So, therefore, for producing in manufacturing processes, for producing the beneficial compressive surface residual stress is maybe most of the cases it is one of the objective of the manufactured component to improve the surface residual stress properties by simply converting or maybe inducing compressive residual stress on the surface. So, the methods can be used simply the short pinning and the surface rolling process can be used to improve the compressive residual stress on the surface. So, short pinning is a local plastic deformation induced by pressure using the kind of small impact, simply impact load by a small ball, or by a roll if we try to impart some amount of the load on the surface, and that actually try to induce some amount of the compressive residual stress, and most of the cases we follow this short pinning and surface rolling method to improve the fatigue resistance properties of a particular manufacturing component. Now, wide variety of residual stress, actually nature of the residual stress, there is a wide variation, and maybe sometimes it becomes very random, and that depending upon the thermal processing used in the manufacturing procedure. So, maybe thermal processing, the application of the heat and the cooling process are completely different and different type of the manufacturing processes. And so, in that cases we can find out that there is a wide variation of the residual stress generation. For example, the surface hardening of the steel, sometimes we in a steel product if there is a necessity for the surface hardening, but if we do the surface hardening of the steel by using some induction hardening. So, on the application of the heat, induction hardening such as carburizing, nitriding, so induce carbides, nitrides, and the quenching process also, carbon steel or similar methods or kind of other similar methods, they can induce some kind of the compressive stresses. So, therefore, sometimes to improve the surface properties we can induce the surface surface hardening, we follow some kind of surface hardening methodology, for example carburizing nitriding, and if we do this kind of methodology by this process we can improve the residual stress on the surfaces. Of course, apart from that, if we follow the other heat treatment process also, so for example, in most of the after welding processes there must be some amount of the residual stress in the component, and most of the cases after welding we normally follow the heat treatment process for particular component. Once you follow the heat treatment process, it actually try to reduce the residual stress up to certain extent, not completely. So, that residual stress magnitude can be reduced by following the heat treatment process after welding, or redistribute the amount of the stress also. So, that is why most of the cases after manufacturing component we can do some kind of the heat treatment process. So, of course, other processes, for example machining such as turning process, milling process and some kind of the finishing processes, they also in such as grinding and honing, that type of machining processes also or finishing processes also induce some amount of the residual stress. So, therefore, surface residual stress normally in these cases, in this machining processes, the surface residual stresses are normally tensile in nature, but in the subsurface residual stresses normally compressive in nature. This is the typical observation of the residual stress. So, this is all about the residual stress. Just I am trying to give some overview of the residual stress, which is very much relevant to the different types of the manufacturing process, and of course, it is a design or practicing engineer, it is always to objectives to reduce the some amount of the residual stress, or at least to induce some amount of the compressive residual stress to improve the fatigue like properties of a particular component. So, thank you very much for your kind attention.